Here we're dealing with a very common problem of a weight being suspended by multiple wires. This problem is commonly found in the chapter of your physics textbook dealing with the laws of motion. So, a mass of weight 325 newtons hangs from 3 wires as suggested in the image on the left. 2 of the wires make angles of theta 1 equal to 60 degrees and theta 2 equal to 25 degrees with the horizontal. If the system is in equilibrium, find the tensions T1, T2, and T3 in the wires. So the first thing we're going to do, which is common to almost any physics problem, especially ones dealing with the laws of motion, is we're going to first draw a free body diagram. So first of all, let's start by looking at the mass m, which you don't really need to know the mass in this case because they already told you the weight is 325 newton c. Okay, so we have a force pulling down on this, and that's equal to W. And we have a tension which is counteracting it, T3. And we know that since it's in equilibrium, the net force on this mass is equal to 0. So let's just say F net equals 0. So because of that, we know that T3 must equal W, 325 newtons. So that's the easy part of this problem. The slightly more difficult part is dealing with these 3 wires here. So they're all acting on the same point in the center. We have T2 pulling off in this direction, T1 off in this direction, and T3 pulling down here. And we know that these three forces must cancel each other because, again, the system is in equilibrium. What we also know is that these, in general, or well, pretty much always, wires will only pull along the direction of their axes. So T3 is pulling straight up and down, T2 is going along this direction, and T1 is going along this direction. And that'll be important when we introduce a little bit of geometry into here. Okay, so because we know that there's a net force of 0, we know that the 3 vectors, T1, T2, and T3, we know that they must sum to 0. So back to what we just drew, we have T1 pulling off in this direction, T2 coming off in that direction, and T3 pulling straight down. And that gives us this equation here, knowing that these cancel. In order to solve this problem, we have to separate it out into 2 components. First, looking at the y component, we know that the net force pulling up, or the force pulling up on this, has to equal the force pulling down. So we know that T3 is only pulling in the y direction, so we can calculate from that that the y components of T2 and T1 must essentially sum to equal to T3. And that's what we have here. So we have T3 is equal to the y component of T1, which in this case is T1 sine theta. This is because if you look at T1, let's draw that here, using some pretty simple geometry, you could see that this angle here is also theta 1, which means that the up and down, or y component, is going to equal T1 sine of theta. Likewise, the y component of T2 is going to be T2 times sine of theta 2. Now for the x components, we get the same thing, only this time T3 doesn't have any component in the x-axis. In the x-axis. So therefore, what we know is that the x components of T1 and T2 are going to cancel each other. Therefore, we set T1 cosine theta 1 is equal to T2 cosine theta 2. So now what do you notice from this? Well, we have 2 equations here, and we also have 2 unknowns. We have equation 1, equation 2, and we have our unknowns are T1 and T2. A few ways of solving 2 equations with 2 unknowns. You could either use some fancy linear algebra and set up some kind of matrix, and use some use some tricky math to try to do that, but the easiest thing to do is obviously just substitute and solve. Once we go ahead and do that and substitute each of these and do that substitution, what we get are two equations, one for T1 and one for T2. Both of these equations are written in terms of T3, theta 1, and theta 2. For T1 we have T1 is equal to T3 divided by cosine theta 1 times tangent theta 2 multiplied by 1 divided by 1 plus tangent theta 1 divided by tangent of theta 2. Now, so T2 equation is actually almost exactly the same. The only difference is instead of cosine theta 1, you have cosine of theta 2, and instead of tangent theta 2, you have tangent theta 1. When you actually plug in the values of 325 newtons, theta 1 equal to 60 degrees, and theta 2 equal to 25 degrees, again, this is W is T3, so T3 equals 325 newtons. What you end up with is T1 equals 295.7 newtons, and T2 equals 164.24 newtons, or something close to that. So before we finish up here, it's always important to double check your work. This is perhaps the most important step. And that's because, I mean, if we go back and if we actually take a look at the equations we just wrote out, they're pretty complicated, and you know, anyone's capable of doing this. It's just that the algebra is a little bit complex, and it's easy to like mistakenly label something. Or maybe when you were setting this up, you included a negative sign somewhere that ended up ruining everything else. So it's very important to check the work in a more simple setting, in a more simplified setting. And a great place to do this is actually just looking directly at the y component equation and the x component equation. So if you plug in T1 and T2 into these equations, they should essentially be satisfied. For this equation, we end up getting roughly 255 for this term, and add that to 69 for this term, and that ends up equaling 324. So that's just because I left off decimal points. If I had included those, it would probably be closer. Likewise, when we compute T1 cosine theta 1, we find that equals 147.85, and when we do T2 cosine theta 2, that's 148.85. So yeah, again, those are almost exactly the same. That's within 1% of each other, so that's good enough for me. Usually if you made a mistake, you'd obviously have a much more significant difference than that.